In this video, we're going to be doing a Unit 8 Fluids FRQ for AP Physics 1. Let's say we have a large vertical tank is open to the atmosphere and contains two immiscible fluids. The top fluid is oil with density oil and height oil. The bottom fluid is water with density water and height water, where the density of water is greater than the density of the oil. A small circular hole of a cross-sectional area, AH, is attached to the side of the tank at a depth 8d below the oil-water interface. So the hole is inside the water layer. Assume the tank is large enough that the speed of the fluid at the top of the surface is negligible. A horizontal jet of water exits the hole and strikes a block of mass m resting on a frictionless horizontal surface a distance L from the hole. After striking back, the water comes to rest horizontally. Derive an expression for the absolute pressure H at the hole in terms of the variables. So first, we're going to start off with the fact that our hole is going to be open to the surface. So because the water here is going to be open to the air, we can see the atmosphere has a pressure of P atmosphere. So we're going to say that the pressure that we have up here at the top is going to be equal to the pressure of the atmosphere. So we know that our pressure is going to increase according to our hydrostatic pressure with this formula, rho G delta H. So first, what we're going to look at is each of the layers. So when we are looking at oil, we can see this will be our interface, and we will say that this is equal to our pressure atmospheric plus rho oil, G H oil. So then if we go down to distance D, we're going to have pH is equal to P interface plus the density of water, GD. So now we're just going to substitute in what we have. So in total, at the hole, we have pressure atmospheric plus density of the oil times G times H of the oil plus density of the water times G times D. So the reason this is correct is because at the hole, we have the weight of both the oil column and also the water. Using Bernoulli's equation, derive an expression for the speed V of the water as it exits the hole. Your final answer should be in terms of these variables. Bernoulli's equation, which is also on your formula sheet, is this. So this is basically conservation of energy, but for our fluids. So this first term here is going to be your pressure. This is going to be your energy term, and this is kinetic energy. This is your potential energy, and same for this other side. So we have that inside of our tank. We are going to have our pressure initial is equal to our pressure at the hole. And our V initial is going to be approximately 0 according to what we consider as negligible as the top of the tank. So then when we are outside the hole, the pressure final is equal to the pressure atmospheric at this point. And your VF is equal to V. So then we can see that inside and outside the points at the same height, that's going to be the same height. We're going to say Y initial is equal to YF. So that's what we are looking at in this case, since we have that the water is shooting straight out. So what we can do is we say that Y initial is equal to YF. So in this case, we can see that our Y's will cancel because they're going to be multiplied by that entire term. So that just cancels out. Now, on this side, this is going to be our height. So we're going to have P height, P hole is equal to atmospheric plus 1/2 rho water V squared. So then after this, we have height minus atmospheric is equal to 1/2 rho water V squared. So we have from part A rearranged this. So then we can substitute that in, and we have so now all we're going to do is multiply both sides by 2. This will cancel out. Next, you can divide each term by density of the water. V squared is equal to 2 times density of the oil, GH in oil, divided by density of the water, plus 2 times density of the water, GD, divided by the density of the water. V squared is equal to 2G times density of the oil divided by density of the water, and 2GD, because this density of the water cancels out. So then after this, we can factor. We can take out 2G. You see that in each term. And then we take the square root of both sides. So this makes sense because our oil is going to add pressure, but the exiting fluid is going to be water. There's pressure from oil. So because water is going to be the actual fluid that's exiting, the oil pressure has to be, the oil pressure contribution must be divided by the density of the water. So the volume flow rate through the hole is QA times V. Derive an expression for the mass flow rate in terms of the water leaving the tank. So we have this area of the cross-sectional area hole. So we know our mass flow rate is going to be our density times our volume flow rate. So then we can substitute this in. That's our velocity there. So this is one of our expressions. We have our speed from part B. So then we can substitute that in as well. So we could take that entire expression for V. And that's our answer. So this makes sense because if you increase your area, you're going to see that you have more mass leave the tank per second. Also, if you increase your density or you increase your V exit. So all of these things means more mass leaves the tank per second. Okay, for our next question, we have that the water jet strikes the block and comes to rest horizontally. Derive an expression for the horizontal force exerted on the block by the water jet. So we know that the water is going to hit the block and come to rest. So that means initially we have V, and then finally we have 0. So then we can use Newton's second law in the momentum form, where our net is equal to the change in momentum over the change in time. So if you have a continuous stream, we can say that F net, your force, is equal to the change in your mass over the change in your time times your change in velocity. So yeah, that's just, by the way, that's your acceleration, right? It's substituted in acceleration for a change in V over change in T. So you can write this as m times Vf minus V initial. So our force on the water is equal to our mass times our final, which was 0, minus V, which is equal to negative mass times V. So what this negative sign means is that the block pushes the water backward. And we know Newton's third law states that the water pushes forward with equal magnitude, because we have equal and opposite pairs. So that means that the force on the water, or on the block, is equal to mv. Same magnitude, just opposite direction. So then if we substitute, we have that m is equal to density of the water times area of the hole times v. So then if we substitute that in, we have this. So then we can just multiply that. So that is how we get our F on the block. We're asked to find the F on block, so we can continue this even more. We know that V squared is equal to 2g d plus density oil over density water times height oil. So then where we see V squared right here, we can sub that in. So we get 2g d plus density of the oil over density of the water times height of the oil. So then you can distribute. We have we can cancel out one of those density of the waters. So then we get this expression. We can factor out 2 times the area of the hole times g. Right here, 2 times the area of the hole times g, 2 times the area of the hole times g. And we're left with density of the water, d, plus density of the oil, height of the oil. So that is this simplified, or this is the form with things plugged in. You could have also left it as this form as well. Either one works. So we can see that the force on the block is coming from the rate at which the momentum of the water is reduced to 0. So suppose that the density of the oil is increased while the height of the oil, distance d, density of the water, and the area of the hole remain constant. Describe how the exit speed of the water changes and justify your answer using your expression from part B. So we had from part B, the V is equal to the square root of this. So if the density of the oil increases, then we see that this fraction is going to increase, because we see that density of the oil is inside that fraction. Therefore, it's going to increase this entire part that's underneath. So that entire quantity underneath the square root is all going to increase. So our V is going to increase. And a denser oil is going to create a larger pressure on our water layer. So that means the water is going to exit faster. Suppose the hole is moved upward so that it is now in the oil layer, but is placed at the same vertical distance below the open top surface as the original hole was below the open top surface. Compare the new exit speed to the original exit speed. So when we had our original hole depth above the top surface, the y original is equal to that height plus a d. Now we have the new hole. We have the same vertical distance below the top surface, which we'll write as y new is equal to height plus d. But the hole is now in oil. So that means that the tank must have enough oil so that the hole must have enough oil above the hole so that the exiting fluid is now oil. So then we are going to use Bernoulli and also Torricelli. So we have the oil is equal to atmospheric plus density oil, GH, oil plus D. So we're going to apply Bernoulli, where one side is going to be the top surface to the oil hole. So when we are at the top, right, we have P1 is atmospheric, and our speed is negligible, approximately. And then at the hole, we have that it's going to be equal to atmospheric again because it's exiting out. And VF we'll call V oil. And our vertical height drop is going to be the height of the oil plus D. So we're going to use the Torricelli result that we get from Bernoulli. That's V oil is equal to the root of 2G times the height of the oil plus D. And that's just our normal. V is equal to 2GH, root of 2GH, where that is our new height drop, where we just substituted in this, essentially. So now we can see that our original water speed, V original, was equal to the root of 2G times D plus density oil over density water times height initial. So we can see that density of the water is going to be greater than the density of the oil. So that means that density of the oil divided by density of the water is going to be less than 1. So at the same time, this entire thing is going to be less than that. So we can see that density of the oil times density of the water times height of the oil is less than the height of the oil. And that density plus, or D plus density of the oil divided by density of the water times height of the oil is going to be less than distance plus height of the oil. So now what we can do is multiply both sides by 2G. So this is therefore 2G. Multiply this by 2G. We get 2G, D plus density oil, density water, height oil is less than 2G times D plus height oil. Now we can take the square root of both sides, and we can see clearly 2G D plus density oil, density water, times the height of the oil is going to be less than 2 times G D plus the height of the oil. So then now we can declare that V oil is going to be greater than V original. This makes sense because we have the same vertical depth below the surface. Our oil is going to exit faster because the exiting fluid is going to be now less dense than the water. So then the gravitational height is going to correspond to a larger speed. Then if we had the original two fluid water exit case where it was water that was exiting the hole. So now the block is initially at rest. If the force from the water jet acts for a short time interval delta t, derive an expression for the speed of the block immediately after that time interval, assuming that the force from the jet is approximately constant during the interval. So we already saw that the force of the jet is equal to delta, or to the density of the water times the area of the hole times v squared from part d. So we also know that we have a frictionless surface that the block is going to be resting on. So we can use Newton's second law, summation of our forces net times ma, where m is going to be the block of our mass, and we have that the horizontal forces sum net is just going to be the jet force. So this is just going to be the force of the jet times ma. We want to solve for a. So we get that a is equal to the force of the jet divided by the m. So if we have a constant force over a time delta t, we get that the v on the block is equal to v initial plus a times delta t with our kinematics equation. We know that we have v initial equal to 0 because the block was at rest originally before it was hit by the fluid. So then we can simplify this to this v block is equal to a times delta t. So then we can substitute in our acceleration, which we just found here. Acceleration is equal to f jet divided by m. So v of the block is going to be equal to the force of the jet divided by m times delta t. So now we know that we have the expression for f jet, right? So f jet over here was equal to this. So then we get that v block is equal to density water, area whole, v squared, delta t, divided by m. So then after this, we can write our expanded form as well, where we have that f jet earlier was equal to 2 times a whole times g, density water, d plus density oil, height oil. So then v of the block is going to be equal to 2 times a whole g density water, d plus density oil, height oil, delta t, all over m. So that is going to be our final answer of v of the block. And this makes sense because our jet gives the block impulse. And we know that impulse changes the block's momentum.